So the next session here is game analytics and visualization, and Maggie, the floor is yours.
Great, thank you. That was a great talk, so it's going to be hard to follow. Thank you all for being here. This is the second session for game analytics and visualization. We're going to start with the player behavior profiling through Povec, I think I'm pronouncing it right, graphs and representation learning. I believe this is a video. And Sydney, are you the one who's going to take questions later?
Yes. Hi.
Great. Hi.
Hello, my name is Sidney Mello. I'm a PhD student at Fluminense Federal University, Brazil, and I'm going to present a paper entitled Player Behavior Profiling through Provenance Graphs and Representation Learning. This is a structure of this presentation: introduction, background, clustering, node embeddings, experimental setup, results, and discussion, and finally conclusion. Due to advances in telemetry, it has become common to remotely gather game session data from players. As a direct consequence, gameplay metrics derived from this data have been used for game design evaluation, UX, and player behavior profiling or clustering. In the case of player behavior profiling, game metrics are often handcrafted features and eventually computed after key events, such as level or game completion. Also, an expert is needed to define which game metrics are suitable for the clustering task. The objective of this paper is to propose an end-to-end approach for player behavior profiling that uses raw data from game sessions and learns a dimensional space in which player actions are clustered, and then assess the validity of this approach. To achieve that, we use the following concepts presented in the background section: provenance graphs and representation learning. Provenance graphs are annotated directed acyclical graphs used to record an object lifecycle. In games, the ping provenance in games framework maps agents such as players and NPCs, entities like weapons and static obstacles, and activities such as actions and events as nodes, and their causal relationships as edges. The figures show a subgraph of a racing game where we can see several attributes of the player avatar extracted directly from its script. Provenance graphs present a rich and raw source of game session data and provide relevant information in its edges, which is crucial for the following concept. Graph representation learning aims at mapping graph nodes to a low-dimensional vector space, considering not only their associated attributes, but also the structural information of the graph it belongs to. With these vector representations, which we call embeddings from now on, it is possible to feed the transformed data to downstream machine learning methods for tasks such as classification, regression, and clustering. In a previous work, we defined a framework for machine learning on game provenance graphs called PingoMil, based on the graph representation learning method GraphSage. Here is an overview of the PingoMil framework considering a classification task. In summary, the proposal of this work is to use provenance graphs that represent raw game session data as input to the PingoMil framework on its unsupervised setting in order to obtain node embeddings for player nodes. These node embeddings represent the player state and its neighboring context and are fed to clustering algorithms to obtain player node clusters, profiles, that hopefully provide insights about player behavior at a fine-grained level. Regarding clustering algorithms, we opt for K-means and spectral clustering, following guidelines from the clustering behavior data paper by Balkhage et al. K-means is suggested due to the overall goal being a general model of player behavior and spectral clustering suggested due to the relational nature of graph data. We prepare an experiment to assess the effectiveness and validity of our approach. As case study, we have captured game sessions for Smoke Squadron, a local multiplayer flight battle game which is still in development. In this game, two players control small remote airplanes and battle with machine guns, 3 different missiles, and a solid smoke trail that kills at touch, creating obstacles in a drone-like fashion. We recorded 37 matches between 4 volunteers, totaling 168,000 nodes. The graph generated are anonymous and it contains the following types of attributes, such as identifiers for the game object, which action is being done, health, movement-related attributes such as position, speed, input-related attributes such as the use of an acceleration trigger or a braking trigger, physics, and also weapons-related attributes such as counters, cooldown, and explosion timers. Now we go to the results of the experiment using Smoke Squadron matches. First, we observe in this figure the whole vector space learned where each point represents a node. As we can see, player nodes were densely grouped into the rightmost section of the space, while other game elements, such as items and weapons, are widely distributed in the leftmost section of the space. The intersection between these two groups contain nodes with similar contexts, such as players and smoke nodes that receive damage, for example. We understand that as an evidence of node embedding's representation power in terms of contextual similarity. Now, we focus only on the player nodes clusters. To understand the meaning of each cluster, we follow 2 steps: statistical analysis of the attributes per cluster and subgraph visualization. We created 5 clusters using both techniques, which led us to these resulting clusters. For conciseness sake, we won't enter in the details of all 10 clusters. It is also not necessary to do it due to some similar clusters between both techniques. After interpreting the clusters as profiles, we understood that k-means generated profiles with less distinctive characteristics, and spectral clustering provided more consistent ones, even improving versions of k-means clusters whenever these clusters share the same region in the vector space. For this reason, we focus on the spectral clustering ones. The bird behavior is characterized by the use of the acceleration trigger, low positions on the y-axis, and few to no conflict-related nodes, such as shooting or taking damage. In this behavior, the player is simply flying in a lower position, which makes the player harder to be targeted. In the figure, the leftmost player belongs to the bird behavior, nodes in blue, during most of its subgraph. The sniper behavior is characterized by the use of the braking trigger, high positions on the y-axis, and at least 40% of missile usage. Here, the player slows down, aims, and fires missiles. However, no death node is registered to this behavior. In the figure, the leftmost player uses the brake trigger, slows down, and fire missiles, which is the green section of its subgraph. The fighter contains 52% of all machine gun shooting, which is the most common weapon. It is also predominant in high y-axis positions, and players usually are full of missiles during this profile, this behavior. It also contains 60% of all the all collisions. In the figure, both players are facing each other. The pink nodes represent the moment where they belong to the fighter profile, shooting one at each other. The hasty behavior contains 60% of being damaged nodes, But even though nodes with shooting or firing missiles are present here, there's not as many as in the fighter cluster. On the other hand, all collisions with smoke objects and 38% of all wall collisions are in this cluster. 86% of item collection also belongs to this cluster. And these observations point out that this behavior frequently occurs during or after a conflict. In the same figure, the leftmost player eventually becomes hasty, the yellow nodes, and ends up colliding with the trail of a missile, which are the black nodes. Finally, we have the victim, which is a pretty obvious behavior. It contains 90% of all death nodes and 30% of the missile nodes, and it mostly fills the gap among other profiles. These clusters could be used to infer non-observed player behaviors into profiles, allowing the developer to know profiles of the players and how the players play, reinforcing or reviewing game mechanics for specific audiences. This experiment, however, contains the following threats to its validity. The choice for the number of clusters is arbitrary and might not reflect the optimal clustering for profile interpretation. Also, the dataset is composed of matches of only 4 players that belong to a restricted demographic. In conclusion, we propose a novel approach for player behavior profiling based on graph representation learning and clustering, which requires no feature engineering or gameplay metrics. We observed that the profile generated could define player behavior throughout game sessions. As future work, we intend to use behavioral profiles generated by our approach as classes for player behavior prediction in-game play time that could be achieved by generating node embeddings during the gameplay session and inferring its profile using a classifier previously trained. We also intend to explore other clustering algorithms such as density-based and hierarchical ones, and also produce a broader and larger dataset. Thank you.
Thank you so much for the presentation. So I'm wondering if people have questions. Until people come up with other questions. I have a question about your data set, and you said, you know, like in the future work, you want to get a bigger data set. I'm wondering what's your data set like now, and what aspects of the data set that you think are not enough that you would want to expand on, and how that will impact the algorithm.
So far, I haven't collected more graphs, but the point about this data set in specific is we have these restricted demographics, which are 4 million white hardcore gamers. So they all learn to play the game during the experiment. So they all learn how to play together. So they probably were using, there were not that much space for creativity when trying to get the better tactic while playing the game, for example.
I see. So a broader audience will probably be very, very different results.
Yeah.
Great. If there's no more questions, we probably are out of time anyway to go to the next talk. So thank you so much.
Thank you.
So the next talk, I believe, is not a video. The deck archetype prediction in Hearthstone. That's either Marcus or Pablo, I think.
Yep. Hello. Marcus. I'm here. Can you hear me?
Yep.
Perfect. Yeah, I don't have a video. I'll do this live. Can you see the slides?
Yep.
Perfect. Well, thank you for the introduction, and yeah, I'm Markus Eger. I'm presenting our paper Tech Archetype Prediction in Hearthstone that I wrote while I was still at the University of Costa Rica with my student Pablo Samo Chacon. And what did we do in this paper? So it says in Hearthstone, so some of you might be familiar with the game. If you're not, this is what Hearthstone looked like. It's basically a card-based game where players build their own decks, and then they have different kinds of cards. Like you have these little guys that are your minions, and you can attack the opponent. You can play different spells that deal damage, that do like different things to either the minions, the other player, to yourself, etc. And one of the things in the game is there are different types of decks. So some players might be playing more aggressively, some players might be playing a combination of cards that, I don't know, wins the game in one turn or wins the game very quickly. Some players might play for the long game, etc. There are 9 different classes that you can play as. Each class has its own cards, its base strategy, and then different kinds of sub-strategies to go from there. And every turn you can play a certain number of cards that's basically limited by like this energy resource that you have. And first turn you only have 1 unit of this energy, so you can only play cards that cost 1 unit of energy. And those are generally the cards that are less powerful. So there's like a lot of different cards out there. There's like 3,400 something different cards out there. Players choose their own cards before they start the game. That defines their deck, that defines their strategy. And the idea is when you play against someone else, you might want to know what strategy they are following. So these decks have funny names, like one of them might be called Quest Shaman, because the Shaman class is playing a deck that is based on cards that are called quests. Or you have a deck called Highlander Hunter. It's the Hunter class, and each card in the deck only exists once. And there are like, well, dozens and hundreds of different deck types that follow different strategies. So what we did in this work is basically, we looked at how can you figure out what the opponent is playing. Why would you want to do that? Because you want to adapt your strategy to what they are doing. So it is helpful. But the problem is you don't actually know which cards the opponent has in their deck. You only know which cards they are playing. So you can only observe the actions the opponent is performing in order to determine what strategy they might be pursuing. And one other thing you have, and we tried incorporating this, I will talk a bit more about this later on, is like how quickly does the opponent do things? As humans, generally, if there are more options, we might need to think a bit more. So maybe if we take into account how long the player thinks, we can determine some information. If they think for a longer time, they might have more options available to them. That means that there are more options in their deck that fit a particular situation. And this is a very subtle effect, which we will see later. Okay. So how did we do this? Basically, we trained 4 different classifiers on 16,000 replay files that we got last fall, so pretty much exactly 1 year ago. And we just looked at what players were doing on the first turn of the game. Because basically, our idea was we want to determine as quickly as possible in terms of duration into the game, what the opponent might be playing. And we collected these replay files, and then we trained the classifiers. The first one is each class has many different deck types, but at any point in time, there's like one deck that is a lot more popular than the others. So a reasonable baseline would be, and that's what we used, just to say like, we assume that the opponent is playing the most common deck for the class that they are playing, because that's also information we have. The second approach we thought about was, well, we can assign prior probabilities. We can basically say, well, the decks have, each deck has this certain probability of occurring, each card has a certain probability of occurring. If we have a particular card, given a deck, we can calculate probabilities for the cards, and then using base rule, we can basically reform that and calculate, given the card, what's the probability for a particular deck being played. And then when we actually see like the cards, there's some math involved with what do we do if the opponent plays more than one card, what happens if we see a card that we have never seen before, etc. You can see the details of that in the paper. But bottom line is we calculate the probabilities for all the decks, given these prior probabilities, and then we predict the one with the highest predicted posterior probability. One approach for prediction that's always popular is neural networks. So what happens is players are limited to how many cards they can play, but there are like certain combinations that allow you to play more than one card on the first turn. I think in our data set it was like up to 6 or 8 cards. So we basically said, well, it's a sequence of entries. We'll feed that to a recurrent neural network as a sequence, and we train that network to predict as an output the deck type. And that has the nice property that it's a recurrent neural network, so we can easily add new features. And one of the things that we added was how much time passes between each of these actions to basically model the player's thinking time in some way. And then we had like these two recurrent neural networks, one that just takes the sequence of cards that were played, and one of them that takes the sequence of cards that were played plus the delay between them, and predicts the tech archetype. So those were the 4 classifiers that we worked with. They got, well, we have various results in the paper. Just as a summary for the presentation, the baseline already got a really good accuracy, and that basically just highlights that there are decks that are super popular. So one of the challenges with this data set is usually players think, or maybe they even write, there's one deck that is so much stronger than the others that most of the players will choose to play that deck. So if we just predict that deck as what the opponent is playing, we already get an accuracy of almost 60%. We did observe, however, that in the cases where players opt for other decks, we can, using our Bayesian approach, increase this accuracy to 78.3, and with the recurrent neural network even to 78.9. As you can see, like these results are very, very close to each other, and they are not, I would not call them like distinguishable in any practical sense. Technically, there's like a small difference between them, but in practice, they're basically the same. The interesting thing that happened is when we added thinking time, that actually reduced the accuracy slightly, but also within an imperceptible like range. So we still got about 78% of accuracy, including the thinking time. So takeaway message for that is basically, looks like the Bayesian approach already works pretty well for this problem. And let me remind you, this is just using what the players played on their first turn, nothing more. So we did not expect, and it would be unreasonable to expect, an 100% accuracy. One other aspect of this though is like, how much do you need to actually train these things? So for the baseline and the Bayesian classifier, this takes a few milliseconds. I think Bayesian takes like half a second on a decent CPU. And I mean, that's pretty nice. For the RNN, we actually, the training takes like half an hour on a graphics card, and then we did a grid search to find like the right parameters. So you can imagine, by having many, many different settings for the grid search, this just takes, I mean, not an obscene amount of time, but maybe we'll have to run it overnight or over the weekend. And the same was true for the RNN, that also takes time into account. By the way, if anyone, what I actually wanted to measure is power consumption, but if anyone knows a good way to accurately measure power consumption for neural network training, please let me know. Because I actually set some students in the class on that as well, and they couldn't figure it out. So I'm not sure if there's like a straightforward way to do that. So one thing that's also interesting, like one of the challenges is we had 16,000 replays that we collected over like a couple of weeks. But the meta game, which decks are popular, which decks are played, changes in Hearthstone. They release new cards, and then suddenly very different decks are much more popular or better or worse, or the entire landscape changes. So we cannot just sit there and wait for 2-3 weeks after a new expansion is released to retrain our network, to have the data to retrain our network. So another experiment we did, and again, details of this are in the paper, reduce the number of replays that we feed to the classifiers. And of course, that will reduce the performance, because now we have less data, we have fewer different deck types that we can even predict. We don't have as accurate of information. But with only 100 replays, the Bayesian classifier already achieved an accuracy of 67.4%. So that's not entirely terrible, given that it has like almost no data to begin with. And the RNN only got slightly over this baseline of 58% accuracy that we established before, and got like 63.5%. So that's another nice result that makes me like this Bayesian approach a bit more. Okay, and finally, one of the challenges we have is errors are not the same. Not all errors are the same. So for example, here you see a confusion matrix for the statistical classifier. And I want to call your attention to two things. There's a deck called Maligos, the Quest Druid, that was never predicted by the statistical classifier. And every single instance where the opponent was playing Maligos Quest Druid was predicted as the opponent playing Quest Druid, which makes sense because the two decks are basically the same. They just differ in a few high-end cards that are played towards the end of the game. And I don't think that's a big problem. But of course, all the metrics just treat it the same as the situation where we have Control Warrior and Aggro Warrior, which are two very, very different deck types. Like one of them, as the name implies, is a very aggressive strategy. The other one is a very controlling strategy. So it would make sense, probably, that distinguishing between those two is more important than distinguishing between Maligos Quest Druid and regular Quest Druid. But we don't have a perfect way to measure that. And that basically leads me to how and why. We had some reviewers that suggested we should look at the least common deck types. So in this confusion matrix, we had the 15 most common deck types. Reviewers said maybe we can look at the least common ones. We did, but the least common ones show up like one time each. So you either have an accuracy of 0 or 100. Not very meaningful. And it did lead us to think about what is a good error? What are the errors that can occur? Is it important if we know this is spell mage, big spell mage? Probably not, but who knows? How about the freeze mage? So if these names don't tell you anything, spell mage uses spells, big spells uses spells, but some of them are a bit more expensive. And then freeze mage uses like particular kinds of spells. Generally, those are pretty much the same. Maybe, who knows? Depends on what your application is. Our stated goal was to build something that AI agents can use to adapt their strategy. But there are other applications. You could say like, oh, we have a stream or some caster of Hearthstone games, and maybe there's like a little box on the screen that says the player is probably playing this deck type. Or maybe a new player is not familiar with the deck types, and we can use this as an aid to actually help them learn the game. And for each of these, like there's different things that are acceptable, different things that are bad. Maybe for the streamers, it would be good if there was like top 5 with probabilities of what's the probability that the opponent is playing this. For an AI agent, maybe we don't really care about the deck name, we just care about very coarse strategies, etc. We haven't solved this in the paper. This is just me musing about what could be done in the future.
Just sorry to interrupt, just 1 minute left. I don't know.
Perfect. No, that's perfect. So the last question I wanted to like pose is, if we use this as a player aid, what's the ethical impact of that? Would this be an unfair advantage of one human player over another human player? We don't believe that just by itself, the work that we did breaks the game, but it is definitely moving in a dangerous direction. So this is something to keep in mind if this work is to be pursued in the future. And now I'm already done. Just like shout out, we used replays from HS Replay. I want to thank them for letting us use the data. Work is not affiliated with them at all. And if you want, you can reach out to me on Twitter. There's another email address here from Carpoli Pomona, where I should be starting in January. There's code available, and you can find the slides on sourcelab.info/FDG2020. Thank you very much.
Thank you very much. Actually, unfortunately, we don't have that many, we don't have actually any time for questions, but I really appreciate the amount of detail, especially the confusion metrics and the discussion around that. I think this is really cool. So I would like to just thank the speaker and move on to the next paper. Thank you. Okay, I think the next paper is a video. It's the probability and graph theory in a board game, strategies and improvements with Ticket to Ride.
Thank you for listening to my talk today. My name is Teal, and I'll be discussing applications of graph theory and probability in the board game Ticket to Ride. For those of you who are unfamiliar with Ticket to Ride, it's a game played on a map where there are cities connected by different train routes. The object of the game is to get as many points as possible, and you get points by connecting routes between cities, and you also get points for collecting destination tickets. Destination ticket is a pair of cities, and if at the end of the game you have a path between the two cities, then you get the minimum number of trains that you would have needed to collect them. If you don't have a path, but you do have the destination ticket in your hand, then you lose that same number of points you would have otherwise received. So today we'll be talking about two broad things. The first is routes. We'll argue that long routes are overvalued and can be used to easily win. And we'll propose a better scoring scheme based off of indicator random variables. The next thing we'll be talking about is destination tickets. Players with some destination tickets perform better than players with others. Why is that? We answer that question and then analyze destination tickets and rank them according to which ones you should choose if you're playing this game. So we'll first discuss current route values. Here we assign points in the way the game is currently played based off the length of the route. If you have found and claimed a route of length 6, then you get 15 points. Clearly, this is more than if you have routes that are shorter, but also on a per train basis, the number of points that you get increases. The arguments for this is that collecting many trains of the same color is difficult. Arguments against this are is it really that hard to collect 6 trains of the same color? And at the same time, the way the game is played, you can only claim one route per turn. So if you claim a route and you're claiming lots of shorter routes, then you're using your turns less efficiently than if you're claiming longer routes, because you can't use the turn that you're using to claim shorter routes to do other things that would help you get more points. And finally, collecting multiple colors simultaneously helps. Yes, it's difficult if you're only collecting a particular color, such as blue, but if you're collecting many colors at the same time, maybe it's easier to get routes that are longer. So these are analytical reasons why long routes are overvalued. Let's look at some empirical reasons. We've simulated 20,000 games of Ticket to Ride with 4 heuristic strategies. And as you can see in this figure, the long route strategy performs the best. It outperforms all the other heuristics, and we argue that's because long routes are overvalued. So the question becomes, if long routes are overvalued, how should we value routes? Our idea is to say that the value of a route, the reward that you get for it, should be the expected time to collect the number of train car cards that you need. And that's measured in the number of cars rather than the number of turns. So to do that, let's introduce some variables. We're going to let n sub k be the number of cards until k blue cards are found. Certainly that's k, plus all of the other non-blue cards that appear before the kth blue card. Then the expected number of turns to find k blue cards is certainly k plus the sum of indicator random variables. We can take the expectation of it. The expectation of a constant is still that constant. The expectation of a sum of independent random indicator variables is simply the number of terms in that sum times the probability that each indicator random variable is 1. And to calculate that probability, we say, think of the deck as non-blue cards separated by blue cards into the number of blue cards plus 1 piles. possibly of size 0, then the probability that a non-blue card appears before the kth blue card is simply the probability that's in one of the first k piles. Because this deck is randomly shuffled, that's the number of piles k that it could be in divided the total by the total number of piles. Let's plug all this in, and we say the expected number of turns to find k blue cards is simply 111 over 13 divided by k. The unit doesn't mean much here, but the point is that this is linear. That means the points that you should get per route, or per route that you collect, should be linear to the length of the route rather than the way it's currently valued. If we want to choose a scalar, we can simulate a bunch of games over these different points per train that we're going to assign, and we conclude that the game is most fun if we choose something between 3.5 and 5. So we've talked about routes. Now let's talk about destination tickets and winning. Recall that destination tickets are pairs of cities, and if you manage to have a path at the end of the game between one city and another, then you get a certain number of points. If you don't have that by the end of the game, then you lose a certain number of points. Here the red lines indicate the expected proportion of wins we would expect if it was completely random. Clearly, it doesn't seem to be random. The Boston to Miami route wins far less frequently than the Montreal to Vancouver route, and let's wonder about why that's the case. So let's look at a map of the board game itself, and we say, okay, what is it about the Montreal to Vancouver destination ticket which makes it so much better than the Boston to Miami one? Montreal to Vancouver is the top right to the top left. Boston to Miami is the bottom right to the top right. The answer seems to be that there are longer routes in the top half, and there also seem to be more paths. So it seems generally to be easier to connect in some sort of way. The Boston to Miami one seems to be the opposite. There seem to be fewer paths between those two cities, and the routes along those paths are far shorter. So what's some sort of measure of difficulty that we can use to assign to this to describe why it's harder to connect Boston to Miami than it is Vancouver to Montreal? The answer that we came up with is effective resistance. Effective resistance is a measure of connectivity between two nodes on a graph. So if we think of the map as a mathematical graph with nodes and edges, then effective resistance is how difficult an electric flow would have to work to get from one node to another. This is the mathematical definition, but what we really care about is the intuition we had earlier, which is that if we have more shorter paths, that means that the resistance is lower, and as we've seen, it's easier to connect this pair of cities. Excellent. So we have effective resistance. Let's look at that in the context of our destination tickets. Here we have all of the destination tickets plotted by difficulty, which is we measure by the effective resistance, and the reward that we get. That's the length of the minimum path between them. We also have a line of best fit, and we'll use this measure of residual, which is the difference between the actual reward and, according to the line of the best fit, the reward we would expect to get for a particular route. We color all of these destination tickets by the difference between the expected proportion of wins. So the lighter the color, the lighter the yellow, the better it performs. And sure enough, number 27 is Montreal to Vancouver, and that performs very well. So how do we explain why the ones at the top perform better? Well, we'll use this concept of residual and argue that if we're able to find a route which is not that difficult to connect, but we get a high reward, then clearly we want that route, and that's exactly what we've done. Excellent. So instead of ranking the destination tickets by the minimum path length, which is the reward that the current game gives you, we'll instead do it by residual, and sure enough, Boston to Miami drops from the middle to the bottom. And if you want to use anything in this talk to win, then you can use the order of these destination tickets to choose destination tickets in the game and do better. So in summary, we've examined routes. We say long routes are overvalued, and we've come up with a better scoring scheme. We've also analyzed destination tickets. Players with some perform better than players with others. Why is that? Again, because the way the destination tickets are currently valued isn't that great, but we can improve that, and we've given you a list of how that should be done. Finally, I want to thank you for listening to this talk, and if you have any questions that I'm unable to answer, please email me at rtlwitter@gmail.com.
Interesting. Thank you so much for the great talk. So we have some, about maybe 2 minutes for questions if people have any. Yes, no questions. Your talk was very clear, I guess. Thank you so much for the talk, and I think we're going to move on to the next speaker. I just wanted to also point out that Discord, there's a lot of discussions in there, and people can post their questions as well there. So the next speaker and the final speaker for this session, and probably for the conference, the next is a closing statement. So, and then they died using action sequences for data-driven, context-aware gameplay analysis. That's going to be presented as a video. And I also wanted to mention that this paper got an exceptional paper, so congratulations to Erica.
Hello, I'm Erica. I'm a PhD student working with Dr. Maggie Saif Al-Nasser in the GUI lab, and I'm going to present our paper, And Then They Died, using action sequences for data-driven, context-aware gameplay analysis. So, games have grown exponentially in popularity and accessibility in recent years. And this is especially true of esports, which have become an industry worth close to $1 billion. These online multiplayer games are frequently updated and adjusted to keep them engaging and relevant, to ensure that they maintain their player bases. But with so much revenue on the line, it is critical that the developers making these design adjustments do so in an informed manner. Thus, many have turned to data-driven techniques in order to gain a better understanding of player strategic decisions and behavioral patterns. Quantitative techniques are among the most popular, using statistics, algorithms, and machine learning to identify player types, gameplay roles, and indicators of victory. These methods can analyze data effectively at large scales. However, they rarely preserve the context from which the data was drawn, which can make it difficult to truly understand player strategies or decision-making, which are often informed by that context. By context, we here refer to the factors inside the game that directly or indirectly relate to the choices the players can make. If one wishes to examine gameplay in a context-aware manner, qualitative methods offer this boon. These usually involve observation, interviews, and other forms of direct communication with players. However, these techniques can be labor-intensive, time-consuming, and really difficult to scale. A number of techniques do exist that are exploring ways of preserving context in quantitative methodologies, but most have yet to be used in domains as complex and dynamic as esports. Previous work addressed this issue with the development of a methodology called Interactive Behavior Analytics, or IBA. This mixed methods approach leveraged two visualization systems. StratMapper was used to display low-level event data in a spatiotemporal context. Superimposed on top of the game map, it allowed users to apply labels to the data that could be exported for analysis. Glyph was used to display the labeled data as a sequence of actions in a node-link diagram, where every node is an action or game state and every link is a transition. The procedure of IBA involves using the context provided by StratMapper to derive behavioral labels that comprehensively represent what is occurring in the data. This is followed by exporting the labeled data into Glyph and then analyzing the sequences. IBA suggests using an iterative process of defining, applying, and testing the Glyph visualizations of labels in order to ensure reliability. However, the labels in IBA are not informed by the data alone, rather they're informed by the experience and knowledge of domain experts. This means that the possibility space for label generation could be as vast as the number of possible strategic behaviors facilitated by the game's design, many of which may not even appear within the dataset. Further, label derivation could become difficult if a game either has no spatial component or is not well known enough to have domain experts. All these elements together make the iterative labeling process long, labor-intensive, and just generally really difficult. It can take hours and hours and an exhaustive number of iterations just to reach a decent reliability, simply because the labels that were derived don't really reflect what's actually happening in the data. Now, you could automate the label application process through AI or ML, but game data is complicated and existing techniques struggle to identify the complexity the way a human can. Further, keeping a human at the center of the methodology can help to ensure that the resulting labels are not only relevant but interpretable by a human. Thus, the work we present here addresses this by adding sequence analysis, an established methodology used in the social sciences for discovering patterns in data based on a sequence of actions, as a preliminary step to IBA. The combined methodology now consists of 3 steps. The first step is the sequence analysis step. In the sequence analysis step, data is abstracted into sequences of actions and visualized using existing libraries. The abstraction at this stage can be derived algorithmically based on information that is included in the data. For example, here the raw data is abstracted into behaviors based on how close or far the given player was from other players at set timestamps. Thus, human labeling is not required at this step. The visualized sequences are then analyzed by domain experts who look for frequent patterns within the sequences and subsequences that convey behavioral meaning. They then use these patterns to develop a list of high-level labels. Coming back to the overview, the next step is refinement, contextualization, and reliability. In this step, the domain experts use StratMapper to refine and contextualize the labels. The temporal occurrences of sequence patterns in the first step are used to direct analysts to certain time points in gameplay within StratMapper. In other words, if the pattern was observed to be near the beginning of a sequence in the previous step, then the analyst will look for it towards the beginning of gameplay. If it was observed to be towards the end of the sequence, they'll look for it towards the end of gameplay. They can then examine what players are doing more specifically and adjust and combine labels to better represent the behavior. They can also derive contextual information by observing what happened before, during, and after each event, and turn these into contextual tags that can be combined with the labels. This essentially creates a rubric of label tag pairs, where the label is the behavior and the tag is some additional context. For reliability, it is recommended to do this in an iterative process with iterator reliability checkpoints. Finally, the last step is label application and analysis. In this final step, analysts can use StratMapper to apply the behavioral labels, which are now combined with contextual tags, across as much of the gameplay as they want. These applications can then be analyzed to draw conclusions about player behavior, and this analysis can be done either in StratMapper itself or with another tool such as Glyph. Now, that was a lot of words, so to better demonstrate the methodology and to better explain the 3 steps I described, I'm going to quickly go over a case study we conducted using data from the game Defense of the Ancients 2, or Dota 2. So specifically, we use this combined methodology to perform context-sensitive analysis of Dota 2 players' grouping and soloing behaviors, and how they changed over time over the course of the game. For this case study, we use log data from 150 players. Dota 2 games can be roughly divided into 3 segments, early, mid, and late game, based on when certain events occur. For our purposes, we mark the beginning of mid-game as the moment when the first tower falls, and the end of mid-game as the moment when the first Tier 3 tower, or the tower that's closest to the team's base, falls. Each player's primitive actions are abstracted algorithmically based on proximity to allied and enemy players, and we use the TrayMiner R package to visualize the abstracted sequences. What you see here is the top 10 most frequent subsequences for each game segment I described. I unfortunately don't have time to explain the entire key here, but a full explanation is available in the paper. By analyzing these sequences, we developed this initial list of 10 labels. Again, I unfortunately do not have enough time in this presentation to go through them all, but the full definitions for each label are available in the paper. We then explored the data in StratMapper, refined the initial list of labels, and added contextual tags. The rubric of labels and tags as it existed after this step can be seen here. You can see how the list of 10 labels was transformed into a list of 4 labels, which each had between 2 and 4 contextual tags. For example, team fighting was a label with 3 tags: objective struggle, retaliation, and focus target. The label marks what the players were doing, while the contextual tags provide some motivational context about why they did it. So they were either fighting over a game objective, like destroying a tower, they were trying to get revenge for something the enemy did, like maybe they killed one of their players, or they're trying to take out a specific hero who's a particular threat. So now when applying labels, each researcher would apply a label tag combination. So for example, team fighting objective struggle could be applied. And this helps capture not only what happened, but some of the context behind why it happened. At this point, we conducted an iterator reliability check, and the IRR was not sufficiently high enough, so we conducted a second iteration of refinement and contextualization. The result of the second iteration is the rubric you see on this slide, and as you can see, the labels and tags have changed a bit. There's now only 3 labels, and assist, which was a label before, is now a tag. We then did another round of labeling and IRR checking, and the result for this rubric was 0.6, indicating moderate agreement, which we determined was sufficient for our purposes. We then applied the labels from the final set to a single Dota 2 match in StratMapper, and were able to observe patterns and trends in how player behavior and the context behind that behavior varied depending on the gameplay segment and the players involved. Due to time constraints, I will only discuss one of the patterns in this presentation, but you can find discussions of all the results in the case study in the paper. So one of the interesting patterns we saw was a notable difference in the context of teamfights between early and late game. In early game, the teamfight label most often occurred with the focus target tag, and the target was often an offensive carry hero. This indicates that the primary condition to gather for a teamfight during early game was to focus a target, and that the primary condition to be focused was to be an offense-oriented hero. By contrast, in late game, the focus target tag was only used for 5 out of 17 teamfight labels. If we look at the design of Dota, we can hypothesize that this strategic difference may be because of carries, a type of hero that starts relatively weak but levels up into a powerful glass cannon. Thus, we can theorize that what we see here is a strategy in which players try to work together to focus on killing carries early, to cut them off from gold and experience and slow their leveling. However, by late game, carries have achieved their maximum power, or they're so far behind that they're just not really a threat, and focusing them's not really that beneficial anymore. Instead, teamfights are fueled by other motivations, such as fighting over an objective. That being said, there are still cases where a single hero will try to push action towards an enemy base and they become a threat and they need to be dealt with, which is why the focus target tag did not disappear completely. So wrapping up, using sequence analysis as an initial step to the IBA procedures helped us streamline the label development process by confining and focusing the possibility space for derived labels to those that have a higher certainty that they correctly represent the behaviors present in the data, and allowing the research team to achieve an acceptable IRR in fewer iterations. The combined methodology was able to uncover strategic patterns in Dota 2 gameplay and capture some of the context that informed them. We believe that being able to contextualize data in such a way is beneficial to developers by providing a clearer picture of not only what players do, but why they do it. Further, while label generation could be automated, sequence analysis benefits from keeping the human at the center of the process, ensuring that the results are human interpretable throughout the entire methodology. While we focus our case study on Dota 2, we argue that this approach is generalizable across various game types and genres, since sequence analysis and IBA have both been used in various contexts in previous work, and all player behaviors in games can be represented as a sequence of actions. In the future, we will explore the generalizability and usability of the combined methodology and evaluate it against existing state-of-the-art techniques. And that is all for this presentation. Thank you for your time.
Thank you, Erica. So I think we have some time for questions. I'm seeing some comments. And the comments are saying don't have any questions. Great. So I think maybe we can take the 5 minutes of break before we go to the closing statement. So I'd like to thank all our speakers, including Erica. And thank you so much for being in the session. And I guess that gives you some time to process. And if you have more questions, please post them on Discord. Thank you.
Thank you, Maggie. We'll take the break and then we'll be back here when the other session closes as well.